I want to talk about some subtleties in dealing with work and energy and the way that your choice of system changes the way that those calculations look. In general, people use work and energy all the time in solving physics problems. It's really important, really cool. But a lot of times people think that, oh, just choose your system is a sort of boring, nitty-gritty detail that you can overlook and ignore. I want to point out here that the choice of system matters, and that even if you are not thinking about it, implicitly you've made a choice, and that's an important choice. And I want to emphasize how that works. So bear with me. I've got here a scenario of a crane lifting a 100-kilogram box off the ground. And in this scenario, I think I borrowed this idea from, it may have been Randall Knight's textbook or something, but it's a good example. What I want to do is consider energy, forms of energy, and possible work in the situation where the crate starts at rest, and then it goes at the crane pulls it up at constant speed until it gets to a height h of 5 meters above the ground, at which point it stops. And I'm going to assume that that'll be the story I look at. My initial situation is going to be the box at rest on the ground. Final is going to be the box at rest 5 meters up. And I want to verify that the work energy theorem holds, that this relationship of conservation of energy and work and energy holds, no matter how I choose my system, but see how it plays out differently in different ways of doing this. And I should say, by the way, I said we're going to assume the whole time that I've just got a crane exerting a constant force on this to keep it going at constant velocity upward. But of course, there will be an initial little jerk of acceleration at the beginning where it starts moving, and a final little jerk coming to rest at the top. If you wanted to replace in the definition of work, where each individual work is force dot product with displacement, if you want to make that an integral of f dot dr, you'd be fine. That would work fine. It's a nitty-gritty detail. This will be enough to get us the idea. So, okay, what I want to do first is consider the situation where I'm going to choose my system to be just the box. So I'm going to draw a little dotted line around my system to identify that as my system. Let me identify this. So my system is just the box and nothing else. And when I look at this, I have to do two things when I'm using the work-energy theorem. First, I need to identify the forms of energy that are going to be relevant in this situation. And second, I need to identify all of the external forces acting on the system, forces that cross the dotted line I've drawn around my box on the picture. So for forms of energy, for a box, I've got these different forms of energy I've listed. Total energy is going to be the kinetic energy, which is just 1/2 mv squared for the object in question. Kinetic energy is definitely a part of our story. I'm going to put down my forms of energy over here. So I've got energy is kinetic energy. Potential energy, I'm following the notation of Tom Moore's book on Tom Moore's 6 Ideas That Shape Physics book here. So I'm using V for potential energy and U for forms of internal energy. We'll talk about that in a second. For potential energy is always defined to be an energy that is between two parts of your system. We're never going to talk about the potential energy of an object with relation to something outside of the system, because that would involve a force crossing the system boundary. And that's not a potential energy. Potential energy is an internal form of energy to things within the system. Our box does not have, if the box by itself is our system, it doesn't have any sort of potential energy with itself. And so we're going to leave out V from our energy equation. Internal energy encompasses a lot of things. If the box were rotating or something, that would be rotational energy, which we're going to treat as a form of internal energy. It's not. If the box burned on the way up or something, it would have a change in its chemical energy. Obviously, it has chemical energy, but it's going to be constant along the way. And so it's between initial and final, E initial and E final, chemical energy of this box is not going to change. And so if that's not going to change in between, I'm just going to leave it out of my energy calculation entirely. I could write down chemical initial, chemical final, and just subtract it from both sides of this equation. So I'm just going to leave it out. That's sort of, you're always leaving something out of your energy equations because you can't ever, what's the nuclear energy, the total nuclear energy of the box, right? You're not going to write down every one of those things. the thermal energy, again, the box is at some temperature. It's got some thermal energy. But in this story, the thermal energy of that box, I don't expect it to change significantly just because it was lifted up a little ways. The thermal energy shouldn't change. So really, in this case, I'm treating the box almost like it's a point particle, a simple point particle with no internal forms of energy, no potential energy. It's just energy equals kinetic energy. That's the story. 1/2 mv squared. That's my energy of my system. What are the external forces? Let me write down that. External forces, to figure out the external forces, I'm going to think of this using a free body diagram as my way of listing sources. But you could just make a list of listing forces, rather. You could just make a list. For energy problems, or not being quite as detailed on free body diagrams as you get to be in Newton's law problems. So what are my forces? So external forces, let me write this down. External forces. Well, first I look at things that break the dotted line and do that. So I guess technically the box is sitting on the ground at the beginning, and the ground is holding it up. But let's imagine the crane is holding the weight, so the box is just barely not touching the ground to keep our life simple. The crane's cable comes down and pulls on it, so there's a tension force upward. If I were going to draw a free body diagram, there is a tension force. I'll call that F sub t for tension force going upward that's acting on that box. And if we start when the box is just barely not touching the ground, just before it's yanked upward, but it's been lifted a tiny bit, and it's at rest. If we start there, then there's no other external forces acting. That's my starting point that I'm choosing. But there is a long-range force. There are no other contact forces acting, but there is a long-range force, the force of gravity, that's pointing down. That's what down means. So force of gravity points down. We've got that. So we've got those two external forces acting on this box. And what do? I guess if we know, once the box is in motion and moving upward, during most of its motion, we know that the box is moving at constant velocity. So constant velocity means during its motion means that the acceleration equals 0. And so I suppose I can conclude that the magnitude of the tension force equals the magnitude of the force of gravity. And we know that, by the way. That's m times the magnitude of the gravitational acceleration. mg is our magnitude of our force of gravity. And so in this case, mg, 100 kilograms, g, the magnitude of g is 9.8 meters per second squared. This magnitude is going to be 980 newtons, kilogram meters per second squared. That's the magnitude of each of those forces. So I've got those two external forces, and that means in writing down the work energy theorem, I need to work out this. I need to find the work due to each one. Force times distance for each of these. And let's see how that plays out. I can say that for tension, so if I want to look at the work due to the tension force, that's going to be the tension force dot product with my distance, which is my, I'll say delta r vector, which is upward by a distance h. And my tension force is also upward, as you can see in my little free body diagram here. And so that dot product ends up just being magnitude of the force of tension times h, which is 980 newtons times 5 meters is 4,900 Newton meters, which is joules. So that's the work done by my tension force. I've got that. Then I'm also going to work out what is the work done by my gravitational force. Well, the force of gravity dot product with that same delta r is our work done by the gravitational force. And in doing that, force of gravity points down, my delta r is up, so they're opposite in direction. That means the dot product gives me a minus sign. Minus magnitude of force of gravity times h. And that means this is minus 4,900 joules. So I've got those two works. What about my energy initial and energy final? Well, energy initial is equal to K initial, which is 0 because it starts at rest. It's 0. And for that matter, energy final equals K final equals 0 because it ends at rest. All right, that's our story. That's what we've got. And so I can check then, how does the work energy theorem look for us? Well, I've got energy initial plus work due to tension plus work due to gravity equals energy final. Does that work out? Yeah. 0 plus 4,900 joules minus 4,900 joules equals 0. Okay, that's it. Again, we're just verifying something that's obvious. Hopefully this makes sense. Now again, because the box was my system, I only had kinetic energy that was possibly changing in the story, and I had these two external forces. We've done that. Next, let's consider another choice of system. Let's consider our system to be the box together with the planet Earth down below. That's kind of a broad thing to say, but if we consider the system to be the box and the Earth, then we're going to find that our analysis looks a little different. So our system is the box plus the planet. And I can look at what forms of energy are relevant first, as usual. I look at the forms of energy. There's kinetic energy. We're not going to worry about the planet Earth's kinetic energy changing. It's so big, one of the things that you can prove if you really want to take time to do it is that unless you're like moving moon-sized things around, the planet Earth isn't going to be affected much by what you do. Its energy won't change much. You can prove that. So we're only going to pay attention to the kinetic energy of the box. Maybe I should have called this kinetic energy of the box and mass of the box around. We've got that. The Earth's kinetic energy is essentially fixed because it's so much larger. Potential energy. Now this is an important point. Because the Earth and the box are now both inside of our system, inside the dotted line I drew around my system boundary, because those are both part of the system, there is a gravitational potential energy between the two. And so I'm going to write this as K box plus V gravitational. I've got that, so that was important. And internal energy, again, in this process, the box isn't going to have its temperature raised particularly, nor is the Earth. The Earth's nuclear energy isn't changing along the way. So even though I should be writing plus U nuclear initial and plus U nuclear final, those terms are going to guaranteed to cancel out. And so these are the only terms I've got. My total energy is kinetic energy of the box and gravitational potential energy between the box and the Earth. And so how does this work out? Well, my external forces. External forces. That's my next step. External forces. In this situation, where the box and the Earth are both within my system, the force of gravity doesn't cross the system boundary. That's an interaction between the parts of the system that's encapsulated by the potential energy there. So instead, that's not one of my things. The only contact force that breaks the system boundary is the cable from the crane. So that's that tension force pulling upward of tension. I guess technically, thinking about it, technically the bottom of the crane is also touching the Earth. And so probably when there's a tension force upward here, there's going to be a force from the crane downward over there or something. Maybe I'll put that in here. F normal force from the crane is pushing downward on my system, downward on the Earth. I hadn't thought about that in advance, but it's there. There's a contact point between things outside the system. And when I say the planet Earth is part of the system, I'm basically imagining everything except the crane. So the ground underneath is part of the system, but the crane itself is not. It works. So these are my forces, and I can look at these. I have to say, okay, for those external forces, what sort of work do I have? Well, I guess I should start by saying, what is my potential energy? I didn't have that before. What's my potential energy? potential energy in this case is going to be, you can check up on a list or something of what the potential energy is. We're going to find the potential energy of the separation here is approximately given for objects near the surface of the Earth. It's approximately equal to the mass of the box times the magnitude of the gravitational acceleration times, I guess, if this is the z coordinate, let me just choose coordinates so that z equals 0 is right here, and my plus z direction is up. Then mgz is my potential energy function, and so that's my v. And then I've got my work due to tension. It's the same story it was before, so I know that that is 4,900 joules. And my work due to the normal force from the crane sitting on the ground, well, that's going to be whatever that normal force is, F normal, dot product with 0. Because that contact point doesn't move in the whole process. That just stays still. So the normal force doesn't do any work at all. That's nice. That's actually generally true for normal forces as long as the ground isn't moving. So okay, we've got that. We've got those results. I can check my work energy theorem. And again, kinetic energy initial and kinetic final are 0. So I can put this together. I can check this out. Let me write down my work energy theorem for this. I have here that K initial plus V initial plus work tension plus work normal from the crane equals K final plus V final. That's what I've got showing up here. Now K initial was 0. We had that before. I guess I don't want to cram things in too much down here. I've already crammed it in down here. Maybe I just write it down. So K initial is 0. V initial, my initial potential energy, mgz here, I define my z equals 0 point to be the ground. That's where the crate started. So mg times 0 is 0. By choice, my initial potential energy is 0. Plus 4,900 joules plus 0 equals K final, we said, was 0 because it's not moving in by the end. And V final, my final potential energy. What's that? mgz is mg times 5 meters. That's actually 4,900 joules. And once again, I guess I didn't put a check mark here to say, yeah, we'd gotten that right. Once again, I've got an equality. My work energy theorem worked. But notice that it's different. Previously, I had two forms of work that added up to 0 to give me 0 equals 0. This time, I have work due to tension of 4,900 joules equals final potential energy of 4,900 joules. So the work energy theorem is still true, but it's shaped differently because of the different choice of system that we've made. So that's how this sort of plays out. But one other example I want to do, where can I write this down? I'll just erase this. The one other choice of system I want to look at and talk about just briefly, this one I can't do quite as quantitatively, but I want to talk about how it would work. The other choice of system that I want to look at is, what if I choose as my system the crane and the Earth and the box? There's my system. It's a much bigger system, right? So choice of system 3 is system is box and Earth and crane. And basically everything is in the system now. What are my forms of energy? Well, my energy here, there's certainly the kinetic, oh, not plus. My energy here is there's certainly kinetic energy. So kinetic energy of the box. Kinetic energy of the box, the crane is going to remain at rest, and since it doesn't change its state of motion, I won't include its kinetic energy. The Earth, as we said before, because it's so much more massive, its kinetic energy does not meaningfully change in this process. So Earth's kinetic energy will be the same on both sides, so I'm going to leave it out. But since the box changes its speed along the way, we've got kinetic energy of the box plus potential energy between the Earth and the box, That's important. That's still important. I could say potential energy between the Earth and the crane, but the distance between them doesn't change. The crane's height above the surface doesn't change. So there's no reason to include a separate V gravity term for that if the height isn't changing. And finally, internal energy. This is an important point. U, the internal energy, certainly the nuclear energy of the box isn't changing any more than it was before. The thermal energy of the box isn't changing, but the crane. The crane has different forms of internal energy, including a tank full of gasoline that it burns while it's doing this work. And if you've ever felt the engine of a car or something after it's been running, maybe not by hand, that would hurt, it gets very hot. So the thermal energy of the crane might change as well. There are forms of energy, in other words, there are forms of energy in the internal energy of the crane that actually are going to be changing in this situation. So I'm going to keep this generic U here that is the aggregate of chemical and thermal energy mostly that's going to matter. So I've got all those forms of energy in the story. External forces, none. There are no forces that cross the dotted line, right? The cable attached to the crate, attached to the box, that's inside the dotted line. It's an internal force. It doesn't do anything. There's the contact point between the crane and the ground. That's internal to the system. It doesn't cross the boundary, so it's not listed as an external force. There are no external forces in the system. So what do we wind up with then? My work energy theorem ends up saying that K initial of the box plus VG initial, I guess I'd written that as plus my initial potential energy plus internal energy initial plus no work terms, that has to equal K final plus VG final plus U final. I've got my internal energy, all those final things. Now, just as before, my K initial is 0. My VG initial was 0 based on our choice of coordinates, just as it was over there. And I've got this unknown U initial, and that has to equal K final, well, it came back to rest. VG final, we already said that VG is 4,900 joules, plus U final. And so in this case, I can immediately say, if I want to find my change in internal energy, if I want to say how did the internal energy change, that's U final minus U initial, subtract U initial from both sides, subtract 4,900 joules from each side, I get minus 4,900 joules. So that tells me that between chemical and thermal energy of this crane, its internal energy dropped by 4,900 joules in the process of lifting this crate, or lifting this box up by those 5 meters. And that could just mean that it burned exactly enough fuel to translate into 4,900 joules of energy. More likely, given that engines are inefficient, what that has to mean is that it must have burned maybe more than that much fuel and increased its thermal energy a bit, increased its temperature in the process. So, but in any case, we can still say that I can't verify exactly how much gasoline was used and how much the temperature changed or something, but I can say that the work energy theorem is verified in this case because raising the block by a certain distance cost us chemical energy. We had to spend energy and fuel to make that happen. That's my story for this version of the system. And what I want to emphasize from all of this is that this is the same equation every time, the work energy theorem every time. It's the same scenario every time, a crane lifting a box. But depending on what you choose as your system, you come up with totally different analysis. 3 totally different ways of analyzing this. All of them work, all of them are true. Each one will answer different questions. And so this one is going to be all force-based analysis without having to deal with potential energy of things. You could measure individual forces along the way. This one is maybe this is one of my favorites because it's sort of an elegant way of thinking about it with as much potential energy stuff as you can. I like potential energy better than work when I can do it. And this one was finally a way for us to get at how much fuel did it cost, what was happening inside the crane to lift this up, and that was part of the story as well. So there are these different ways of looking at the same system. I think it's pretty cool that the same equation, the same concept, has these different forms. And again, it all just matters what system boundary did you choose, and how does that affect what things are external forces, what things are potential energies, and what internal energy is relevant in the story.